Good morning, welcome to the 7th video of this course on advanced computer algebra. We are in the middle of the discussion how to exploit fast multiplication and fast arithmetic. We have developed algorithms for fast multiplication and fast division in the first part of the course, and now we are in the second part of the course and want to see how the ability to multiply quickly helps us in solving other problems quickly. We have I want to give you two examples for how to do this, an easy one and a hard one. We did the easy one last time and we'll do the harder one today. The easy one last time was evaluation and interpolation. So evaluation means multi-point evaluation. You have a polynomial of degree n and you want to evaluate it at n distinct points. If you do this naively, it causes a quadratic cost. But we have seen that you can do it more cleverly, and then you get a cost that is just a logarithmic factor more expensive than a multiplication time. And we also were able to solve the problem of polynomial interpolation at this speed. So that means if you have given n evaluation points, pairwise distinct, and n values that your polynomial should have at these points, and you can construct the unique interpolation polynomial of degree at most n or less than n that satisfies these requirements with a time that is also just a multiplication, a logarithmic factor worse than the multiplication time. And how did we do this? So we have seen that standard algorithms that have a quadratic complexity based on the standard multiplication algorithm will also have quadratic complexity if you just replace the standard multiplication algorithm by a fast multiplication algorithm, because the structure of the computation in the standard algorithm and the classical algorithms is such that fast multiplication can't really take off. So you have a lot of multiplications, but they are all very small multiplications, or more precisely, they are multiplications of something big with something small. But if you multiply something big with something small, then it takes linear time to do this, and you don't need a fast multiplication algorithm for this because it just takes linear time. And you can't get faster than this even with a fast algorithm. The problem is that this linear time computation, you have to do a linear number of times, and that's where the quadratic complexity comes from. So that's something that you have to somehow avoid by reorganizing the computation. You want to reorganize the computation in such a way that instead of many small multiplications, you want to do a few big multiplications. And the way how to obtain a few big multiplications, there's a standard advice for the design of such algorithms, and it says divide the problem in the middle into roughly equal sizes, and then solve these problems recursively, and then combine the solutions. And usually in the combination of the solutions that come back from the recursion, you will see that you will need a multiplication or a division. And for the multiplication or the division, you will have then a balanced product where from each recursion side there's something big coming back, and then you have to combine these two big things with a multiplication or maybe several multiplications. But that's good because these will be balanced multiplications of big things with big things, and this is where fast multiplication can show off and really give an advantage over the classical multiplication. So to say it differently, you can also say that you reorganize the computation in such a way that you are shifting a work that you do in the classical algorithms just by hand, but you are shifting it into the multiplication. You want to move as much work as possible into the multiplication, and there it's happening quickly because we have done the work at the beginning of the course to ensure that multiplication can be done quickly. So dividing a problem in the middle can be harder or easier. And a case that we studied in the previous video, the evaluation and interpolation, this is a case where it's relatively straightforward how to divide a problem in the middle. The other example I want to show you, we discussed today, is how to do this for computing the greatest common divisor of two polynomials. That's obviously a problem that needs no further motivation. It's a very fundamental problem in computer algebra, computing the greatest common divisor of two polynomials. And we are faced with the same situation, that the standard algorithm has a quadratic complexity, and it's not going to change if we change standard multiplication by fast multiplication, unless we do something about it and reorganize the computation. And you will see this will be a bit tricky and a bit technical. I'm sorry for this. I try to avoid the technicalities as much as possible, but we still want to see in detail how it works, and so that's a bit of a balance that I'm trying to achieve. If you find that the video and my explanations are not detailed enough, then let me remind you that the full details are in this wonderful book by von Garten and Gerhard, The Bible of Computer Algebra. And if you look up the chapter there about the fast Euclidean algorithm, then be sure that you have the third edition of this book, because they updated and changed and I should say repaired this chapter in the third edition. So there are some bugs in the earlier editions, and they have also changed a bit of the notation, so don't get confused. If you are in an old edition, check the third edition of this book. All right, so let's get going. The task was to compute the GCD of two polynomials, f and g, of degree less than n. We have seen the first few slides already at the end of the video, so we can go through them a little bit more quickly, but still let's recall what we already said. Here's the standard Euclidean algorithm. It it maintains a pair of polynomials that is initialized with f and g, the two input polynomials, and then updated in a loop that runs for an unknown number of iterations. It has a termination condition of which we know that it will at some point be fulfilled. The termination condition is that the second component is 0. When the second component is 0, then the first component is the GCD, and then we stop the iteration and return it. And anyway, if the second component is 0, then we cannot continue anyway, because here we have a division with remainder by the second component, and if that's 0, then this is the division by 0. On the other hand, we can repeat this update whenever it's non-zero, so there's no problem as long as this is non-zero. We can always divide, and the remainder will always be smaller than the thing by which I divide, so I'm replacing always this component by something that is smaller in degree, and so I'm doing also here. And that's why I know in advance that this will eventually terminate. I can also give a bound. The bound is the degree of f, because if it goes down by one step at least in every iteration, then after n iterations at latest you will be done, but you may be done earlier. All right, so here's an example. You don't need to see this again. And here's the graphical illustration of this example. F and g are the input polynomials, and then h and g is starting up here and then walking through this so-called polynomial remainder sequence until you hit a 0, and then the last thing that was not 0 is the output. And I already said that this is called a polynomial remainder sequence, so I will use the notation R for the entries of the sequence, R0 and R1 for f and g, and then the other r's for the subsequent remainders until there's some remainder which is 0. Okay, here's the definition again, and I will use a color code in this video that says that, I will consistently use yellow for the remainders, because there's a little bit of notation needed later on, and so that we don't get confused, I try to support it with colors. Yellow will be the remainders, and we will use blue for the corresponding quotients. They are here. To every remainder there corresponds a certain quotient in the division with remainder, and I call them Qi and draw them in blue. Here's the connection between the R's and the Q's. The remainder of tomorrow is the remainder of yesterday divided by the remainder of today, and this is the corresponding quotient. So it's a minus because you may want to put that on the other side and say this divided by this is equal to, this one is equal to this times the quotient plus the remainder. Okay. And we have also discussed that there's a way to write this as a matrix vector product. So this is very instructive. If you write it like this, then you see how the pair of a certain iteration is obtained from the pair of the iteration just before. What happens is that the second component, the old second component, becomes the new first component, and the new first component is obtained by this division with remainder, and it is therefore a linear combination of the two previous remainders. Here there is an invisible 1 here, so we have 1 times this minus q times this, and this 0 and 1 just moves this one up to here. Okay, let's call these matrices Qi and observe that we can iterate this. So this equation here represents just one iteration in the Euclidean algorithm, but there will be several iterations, and by making them all explicit with the corresponding matrix vector, we can see how the pair in the ith iteration is obtained from the original input. It's obtained by just multiplying all the matrices of all the iterations to the input vector. So this is the matrix from the first iteration and from the second and so on up to the last one, which I have written here. And and then also if you do this far enough, then you will reach the final output, and the final output is when you down here have a 0, and then this is the GCD of f and g, and I don't know in advance how many q's I will need. I just know that there's a certain number, and let's call it eta, this number of q's. And if I multiply all these q's together, then I get a certain matrix R. And multiplying these q's together, that's not what the Euclidean algorithm does. Multiplying these q's together is not what it does. What it does is it computes, it multiplies these q's one after the other on this vector. That's what the classical algorithm does. But it's also okay because of associativity to first compute the R. Maybe somehow, if we somehow get the R, then we are also done, because the R will be a matrix such that multiplying this matrix to f and g directly in one shot gives me the h and the 0. And okay, the q's have very small polynomials. Usually the q's will be small, and the 1 and the 0 and the 1 are certainly small. But if I multiply a lot of small things, then the entries of R will not be small anymore in general. But that's good, because we want to compute with big things, preferably, because we want to get fast multiplication busy. So you have to think of the R as a 2 by 2 matrix where the entries are very big polynomials. Of course, not just this entry down here, but all 4 entries, because when I multiply lots of matrices of this form, then not only this one will get more complicated, but all entries will get complicated. Okay, so knowing the R means knowing the result, and actually we know more than the result, as I already also pointed out in the previous video. We have actually the solution of the extended Euclidean algorithm, because the first row of R contains the polynomials s and t such that h is equal to s times f plus t times g. So that's exactly what the extended Euclidean algorithm provides. So if we can get the r somehow efficiently, then we not only have the GCD, but also the cofactors at the same speed. All right, so the idea is to compute this product of q's, and to do so by splitting the product in the middle. That's the idea for a fast algorithm, but it's unclear how to do this. We don't know the q's a priori. We don't know them at the beginning, unlike last time where we had all the evaluation points as part of the input and they all contributed to the leaves of a multiplication tree, and I can compute the multiplication tree ahead of time and then work with it. Here we can't do that because these quotients, they arise only, I see them only during the execution of the Euclidean algorithm, but I don't want to execute the Euclidean algorithm because it's too expensive. I want to improve it so I can use this approach. We'll have to somehow find escape from the necessity to compute, to follow the instructions of the Euclidean algorithm. I have to do something different. Actually, we don't know even how many q's there are. I called it eta in the previous slide, and we don't know what eta is in the beginning. So how can we break the product in the middle if we don't even know either the factors or even the number of factors? Here's the key. The key is that the quotients depend on the remainders from which they are obtained, but I don't need the full information of the remainders. So here's a typical situation. You have very long remainders in yellow, but you have a very small q that connects these two remainders and leads them to the next remainder. So all these coefficients are necessary in order to compute the q and the next remainder. But if I don't need the next remainder but only the q, then you can observe that the lower order coefficients of the remainders here and there don't really have an influence on this q, provided that, like shown here, the q is small and has only few coefficients compared to those. And that means I can drop them. Why do I carry along these long remainders if I don't have to? If they don't have any influence on q, I can just remove them, and then I'm computing not with the remainders but with some related polynomials that are such that I don't get the real remainder that I wanted to get. But I'm also not interested in this remainder completely. I'm interested only in q, and I get the same q, even though I've dropped most of the data of the input. Okay. So in order to formalize this, let's introduce a bit of notation. Here I define for an integer k and a polynomial f of degree n what it means to chop. So I define this operation. This symbol here looks like a knife a little bit. So I'm chopping off from f the uppermost k terms. I can express it like this. So I read this as f chop k, and it's defined as this polynomial of degree k whose top coefficients agree with the top coefficients of f. Okay, so here, if I write it with, I can write it with this quotient of f by a monomial, but I'm assuming here, if I write it like this, that the k is at most n. So if the k is more than n, then this would be a negative exponent and I don't have a quotient. So it's not, that's not what I mean. One observation is sorry, that if you multiply the polynomial by some monomial and then chop, then it doesn't have any influence on the result. You can just as well just chop the polynomial itself. because the multiplication by a power of x just moves the coefficient array to the left, but here you are taking just the top of the coefficient vector, no matter where it is. If you shift it, it won't affect the coefficients, and this here it depends only on the highest order coefficients of f. So my chopping is ignorant with regard, is ignorant with respect to multiplication by x to the I. And another thing is, if you chop nothing, well, then there's nothing left. So if you, in accordance with this definition, if k is less than 0, then f chop k should be 0. And also, if the k is greater than n, then, well, then and that's not exactly right. So then f chop k is x to the n minus k. No, k minus n times f. So it's the same coefficients. You're not removing any coefficients in this case, but you are here just shifting the coefficient vector of f to the right. All right. So now it's yeah, I'm sorry. This is very interesting, but it's a bit complicated. So I want to compare now two runs of the Euclidean algorithm, one with the original given data f and g, and one with data that is modified, where I'm modifying the lower order coefficients. And modifying will later mean I will just remove them, so that I have to deal with smaller polynomials. But when I do this, then I need to understand how does how does this change the flow of the Euclidean algorithm. So the question is, if I compare an execution of the Euclidean algorithm with this pair, applied to this pair, with an execution that is applied to this pair, then how much will the next remainder agree if these polynomials agree to some extent? Okay, so this is what I want to express in this definition. So I want to say first in this definition that this pair of polynomials and this pair of polynomials is equal in the top coefficients. So I take these two polynomials. They may not have the same degrees. I'm assuming the degree of f is at least as much as the degree of g, okay, and the same here. And then I say that f and g, the pair fg, coincides up to k with the pair f bar and g bar if the topmost k coefficients of f and f bar agree, and the topmost so many coefficients of g and g bar agree. And then I say that these pairs coincide up to k. This is the notion which is defined in this definition. Now here's a picture. F and g are yellow, and f bar and g bar are white. And to coincide up to k means that here this expression takes into account that the g will be smaller than f typically, if I'm thinking of this pair as an instance of the pair that you have during the execution of the Euclidean algorithm. So what I mean here is I take the f and consider the first k coefficients, and from the g I take not the first k coefficients, but I take somehow the corresponding number of coefficients. That's k minus the degree difference. So that's exactly this one, k minus the degree difference. Okay, and to coincide up to k means that the coefficients in this area here of f and g are the same as the coefficients of f bar and g bar in this area, and I don't care what about these coefficients. Okay, so the question is now, what happens if I do a division? So the next row in the Euclidean algorithm, or the next quotient or remainder, will be obtained by dividing f with g, and it will be something smaller than g. And I can as well do division here and divide f bar by g bar, then I also get a remainder. I want to make now a statement about how much the next pair of the Euclidean algorithm, which consists, instead of f and g, it consists of g and this division remainder, how much they agree, how much they coincide, if I assume that there is a certain that f and g and f bar and g bar coincide up to a certain k. Okay, this is an equivalence relation. It is easy to see, but here's now the theorem that we'll have to discuss. So let's go very slowly through this. We assume we have two pairs of polynomials, like in the definition on the previous slide, and we assume that there's a k such that these two pairs coincide up to 2k. Observe that there's a 2k here, and we also assume that the k is bigger than the degree difference, and that the degree difference is at least 0. Next, we define the quotients and the remainders, one for f and g, and one for f bar and g bar. So those ones we call q and r, and those ones we call q bar and r bar. Of course, this is division with remainder, so that there is a degree constraint on the remainder. The remainder must be smaller than the degree of g, and here of g bar. And g is non-zero, so we can do this division. Okay, this is the assumptions. These are the assumptions of the theorem. And what is the conclusion? The conclusion is that if this is so, then the two quotients agree. So this is something that we will find useful later, because it means that if I want to have the quotient for this one, then I can obtain it by instead computing the quotients of this one, and these ones will be obtained from these ones by chopping off everything that is unnecessary. And this theorem tells me how much I can chop off without affecting the equalness, the identities of the quotients. Okay? But then I want to do this several times, so I want to iterate this. And in order to iterate this, I need to understand how this agreement of the coefficients propagates to the next pair in the Euclidean algorithm. And the next pair has here the g, and here this r, and this one has here the g bar and here the r bar. So I need also a statement about how much g r and g bar r bar coincide. And this is also part of the theorem. They coincide up to 2 times k minus the degree of the quotient. Here it doesn't matter whether you take q or q bar, because they are the same anyway. But that's only one possibility. It could be also that the remainder is 0, and in this case this is a meaningless statement. So it's also a case that can happen. Or it can be that you have here a division that is so much that you have an unusually high degree drop in the remainder. And if the degree drop is more than as indicated by this inequality, then this is also not true, or does not need to be true. So we are claiming two things. First, under these conditions, the quotients agree, and in addition, there are 3 cases: r equals 0, or some inequality about the degrees, or the next pair in the Euclidean algorithm still has a certain amount of coincidence in the top coefficients. So let me show you why this is true. This is not an obvious statement. It requires a little bit of calculation to see where this comes from. Proof. So first, let's prepare this a little bit. We can prepare this without loss of generality, making some assumptions to make it a bit more comfortable to walk through this proof. Without loss of generality, we can assume that the degrees are equal of f and f bar, and that the degree is greater than something. And I can also assume that the degree of g and the degree of g bar is equal. So this is an assumption I can make, because if not, then multiply the polynomials by suitable powers of x. We have seen when we discussed the definition of this chop operator that the chop operator doesn't care if you multiply the polynomial by a power of x, because that just moves around the coefficient array, and we don't care about the position of the coefficients, but just about the highest coefficients, however high they are. Okay, so then what we can say is that the degree, we just made sure by assumption that the degree of g bar is equal to the degree of g. And by one of the assumptions, so let me copy the assumptions here. Here I have the assumptions that that these two pairs coincide, and that the k is at most this one, so at least this one. So let me copy this. K is at least degree f minus degree g, and this is non-negative. And then this condition, let's also say what this means. This means f chop 2k is equal to f bar chop 2k, and g chop 2k minus the degree difference, 2k minus degree f minus degree g is equal to g bar chop 2k minus, and in this case degree f bar minus degree g bar, but we have arranged things so that the degrees are equal, so we don't need to worry about the f versus f bar in these degree specifications. Okay, so these degrees are equal, and now I use this inequality here to say that the g is at least the degree of f minus k. So I get this by moving this one here and this one there, and this is non-negative. Okay, and also I know that if I write it down like here, I have k is at least degree f minus degree g, but the degree f minus the degree g, this is the degree of q, and we said that this is non-negative. Okay, so with this preparation I can now investigate what I can say about the degrees of the differences of the original polynomials and the corresponding barred polynomials. So in particular, first it's f minus f bar. What can we say about this? Now the degree of this is at most, or actually less than the degree of f minus 2k. Why is this? That's because these two polynomials, they coincide in the first 2k coefficients by assumption, and by other assumption they have the same degree. So if I take their difference, then there will be a lot of cancellation, and it will be at least that much cancellation. So the difference that remains must have a degree that is smaller than all the terms where there happens a cancellation. Okay, and now if I combine this with these inequalities, then I get that this is bounded by the degree k, the degree g minus the degree of k. Why is this? I use I use this inequality here with one of the two k's. So I have degree f minus k minus k. Degree f minus k gives this one, and the other k remains here. But then this one is less than or equal to the degree of g minus the degree of q, because here we said that the k is at least the degree of q. So if I say minus k, then it becomes at most the degree of minus q. That's the first thing. Okay, now the second thing is about g. What can we say about g minus g bar? Now we can do a similar reasoning here. Here we have just more complicated expressions for the degrees, but otherwise it's a similar thing. It's the degree of g minus the number of terms that cancel because of the agreement. And the number of terms that cancel is this, 2k minus degree f minus degree g. Okay, so if we simplify this, then minus minus gives plus, so this is degree f here, minus 2k, and here we have degree g minus minus minus, so this cancels. And we see that this here is the same as this, so we can continue above and conclude that this is also bounded by the degree of g minus the degree of q. Okay. And then we also have to compare the degrees of the remainders. Now we don't know much about the remainders, but fortunately we don't need to know much about the remainders. We can say that their degree is at most the degree of either of them. So like this. And we can be sure that this is less than the degree of g, because they are the remainder of a division by g. So this one is a remainder of a division by g. This one is a remainder of a division by g bar, but g and g bar have the same degree. So this is the same as g bar. Okay. So remember what we wanted to show. Let's go back after this calculation to see what we wanted to do. We wanted to prove first that q and q bar agree, are the same, are equal. I want to show this now by comparing these two equations. Let's consider the difference of these two equations, because then we get the difference of f and the difference of g and the difference of r. And for these quantities we have just now derived bounds on the degree, and they will allow us to make a conclusion about the q and the q bar. Okay, so let's see. F minus f bar is equal to q g minus r plus q bar g bar minus r bar. So now I don't know yet that q and q bar are equal, but I want to combine these two terms, this one and this one. I can do this by adding and subtracting something. For example, qg bar plus and minus qg bar, and then I get here that this is q g minus g bar plus, so this is from here and here, plus q bar minus q g bar, this is from here and there, minus no, sorry, this is minus, this is plus, and this is minus. Did I mess something? So this with this is this. not correct. This should be minus and this should be plus. Now this one with this one is also not correct, so the bar should go here. Okay, and then plus r minus r bar. Now I hope it's correct. Now let's look at the degrees. We still have the degrees here, so we can estimate them. Here the degrees. The degree here is less than the degree of g minus the degree of q. And that's certainly at most the degree of g. So that's all what we need here. And here we have said that the degree difference of g and g bar is at most the, not the degree difference, the degree of the difference is at most this one here, degree g minus degree q. But now I multiply this with q, so altogether this is at most the degree of q. Okay, now this one is equal to the degree of q, the degree of g bar, which is by assumption the degree of g, and all those ones we said that they all have a degree less than the degree of g. Okay, so let's call this equation 1. We will later need this. If you look at this equation, then you see everywhere here, this one has degree less than g, this part has degree less than g, and this part has also degree less than g. Yeah, I should say here, to be more careful, I should say this is, first of all, this is g, and secondly, this is less than g, because here I have less than. I shouldn't copy from here, I should copy from here. So this is less, this is less. So the red parts have degree less than g, whereas this blue part here has a degree that is the degree of the difference of the q's plus the degree of g, and this doesn't match. This is at first you think it's a contradiction, but it's not a contradiction. It's only a contradiction if this here is not 0. Because if this is not 0, then the degree is non-negative, and then this degree would be at least g. But it doesn't match with the red ones, because the red ones together, if you bring them on one side, all the red ones on one side and the blue one on the other side, then you have an equation that says something that has degree less than degree of g is equal to something that has degree more than the degree of g, and this of course cannot be. So the only possibility is that q and q bar is equal, or the difference is 0, so that they are equal. And that's what we wanted to show. We wanted to show that they are equal. Okay, so then we have shown the first part of the theorem, and now we have to show the second part of the theorem. So for the second part, we have to show that there is one of 3 cases happening. We show that if this is not true and this is not true, then this must be true. So let's assume that this is not true and this is not true. So this is okay. And now next assume that r is not 0 and that k minus the degree of q is at least the degree of g minus the degree of r. And we have to show that if these 2 cases do not happen, then the third of the possible cases happens. And the third of the possible cases was that the pair GR agrees or coincides with the pair G bar and R bar up to 2 times k minus the degree of q. And this means, yeah, there are 2 things to show. Let's call them 2 and 3. And the second says that the G chop 2k minus degree q is equal to G bar chop 2k minus degree q. So I'm just writing down the definition of this equivalence relation. It says that the first two components agree up to so much, and now I will write the second components agree up to so much minus the difference of the degrees of G and R. So I will write R chop, okay, 2k minus degree Q minus degree G minus degree R is equal to R bar chop, same amount of terms, 2k minus degree Q minus degree Q minus degree R. So the second one we don't need to show because we already know it. We have seen that here because we know that the degree difference of f and g is exactly the degree of the quotient, and here also. So this is the this here is the degree of q. So this is for free. This is part of the input. This is part of the assumption here that says that these two pairs agree up to 2k. Well, that includes the assumption that the G and the G bar agree up to as much as I'm claiming here. So only the other condition requires an argument. So 2 is immediate from fg 2k f bar g bar, because the degree of f minus the degree of g is the degree of the quotient. Okay, but for and now for 3 we have this equality that we have derived above here and can use that again. So we what can we say about the degree difference of R now that we know that the blue part is 0? So we know that the degree of R and R bar, the difference of them, is bounded by the maximum of this one and this one, because this one is the difference of this one minus this one. So let's see how much this is. So this is the degree of f minus f bar on the one hand, and the degree of q plus the degree the degree of the difference g minus g bar. Okay, so we estimated them already and saw that this here is less than the degree of f minus 2k. That's again by this assumption here. And here we have that this here is bounded by this one. So this is less than the degree of g minus the degree of q. That's nice because that means this cancels with this. And okay, that's correct, but not what I need. I'm sorry. I wanted to have a different estimate here. G bar. Okay. I want to use this one here. It's also true. So this is less than, then it matches with this. So this is the degree of f minus 2k. And we see it now what the maximum is. The maximum is the second one because they are the same, except that here this comes extra. So altogether this is less than the degree of Q plus the degree of F minus 2k. And what is the degree of F? Yeah, the degree of F, you can say this is the degree of Q plus the degree of G, because Q is the quotient of the division of F by G. So we can combine those two and find that this is the degree of G from here, minus, and then 2 times K minus degree Q. Okay, so what do we want to show? We want to show that they agree up to so much. So we want to show that the degree of the difference is R, is bounded or is less than bar minus this much. Okay, so we are not quite there, but now we just have to rephrase this a little bit. So let's write this. Let me write this first, and then we see if it makes sense. So it is R minus then what it is supposed to be, 2k minus degree Q minus degree G minus degree R. Okay, so that should be this quantity here, and see if this is true. So we have the degree G, which is here, and it's minus minus, so this matches. Then this here is this here, together with the minus, and then this R minus 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 gives 0, so 2. This is this completes the proof. And let's go to let's go back to where we came from and what we wanted to do. Our goal was to compute this product of matrices for a certain polynomial remainder sequence. And what we have achieved now is we have analyzed a single step in the Euclidean algorithm, the error propagation in a single step of the Euclidean algorithm, if you regard the chopping as a form of approximation. So the F bar and the G bar are somehow approximations of F and G, of course not in the sense of numerics, but in the sense of they contain a part of the information of the other polynomials. Okay, so now we take not 2 consecutive remainders, but we take the whole polynomial remainder sequence. So we have the yellow ones, they are the real ones, and then we have the barred ones, and we compare them with each other. So we will ask what happens if the first pair agrees up to a certain k, then how far can I go into the Euclidean algorithm and be sure that all the pairs that come up to a certain point, and which point, that's the question, will coincide, and by how much will they coincide. So this is a question that I cannot answer in general, because it depends on the degrees of the Q's and the Qi's, which usually are 1, but they are not always 1. So I have to be a bit careful in this analysis. And in order to express this, I have to introduce some more notation. Very sorry for this. We say that for a polynomial remainder sequence R, we define eta of k as the number that is such that the eta kth remainder is let's say differently, that if I take the degree of R0 minus k, that this is the degree between the etath and the eta plus first row. in the polynomial remainder sequence. There's a picture on the next slide, but let me just say that I define the same thing for the barred sequence. Remember, we compare two polynomial remainder sequence, this one, and I have the eta that refers to the yellow ones and the eta bar that refers to the barred ones. Okay, so here's a picture. This is a polynomial remainder sequence, and including the quotients written here in blue. And now I take a certain k and say I'm only interested in what happens in this region, not interested in what happens here. And then the eta is defined as this number of rows before the sequence of remainders falls behind the red line. This is the definition of this eta, and it depends on the k, but it depends also on the quotients. You see in the picture some quotients are smaller and some are larger, so I can't just say, oh, this is a triangle, so when I know k, then I know eta of k. It's not quite that simple. But of course, if the k is smaller, then the eta is also smaller. Okay, and now there's a theorem which is in fact just a corollary to the theorem that we spent a lot of time proving just a few minutes ago. This theorem says that if you have two pairs of polynomials that coincide up to 2k for a certain k, then the etas agree and all the quotients up to eta agree as well. Okay, so here's again a picture. It says that you have here you have here the r's and the q's, and you are interested in this region, but there's a 2 here, and the 2 says that you should start with this accuracy, and these coefficients here, these you can drop. If you drop these coefficients and then you compute the remainder sequence, then you will lose some accuracy here, but you will get everything right up to here, and that's exactly the eta. So if you compute with the modified ones, you get the same result up to here, and that's exactly what the definition of the eta is. So let's see why this is true. Proof. We proceed by induction. So this is one of these proofs that have an induction that doesn't go to infinity, but it's an induction that starts at 0 and only goes to eta. But nevertheless, it's an induction proof, so let's go for it. By induction, on J, bounded by eta of k, we will show the following. So we will show something that is a little bit prepared so that I can get more easily through the proof, but which is also so that it implies the statement in the theorem. The theorem is stated in such a way that it's more easy to use. So I'm formulating the theorem here as follows. First, J is less than eta bar of k, and qi is equal to qi bar for all I up to j, and so this and this and j is equal to eta of k, or rj plus 1 coincides up to 2k minus the sum of from 1 to j, the degree of qi with rj bar and rj plus 1 bar. Okay. This is prepared in such a way that once we have shown this for all k up to and including eta of k, then from this the theorem will follow as it is stated. Here we have an inequality only, so the J is bounded by this. So here we get only that eta is bounded by eta bar, but the theorem is symmetric about what is barred and what is not barred, and therefore it's sufficient to just show the one-sided version of this theorem. So the claim follows from here by symmetry. Okay, so now let's go through the induction proof, and for j equals 0, there's nothing to show. Because the statement is empty in this case. And now let's look at the induction step. For j implies j plus 1. All we have to do is to apply the previous theorem, because an induction step corresponds to one iteration in the Euclidean algorithm. And what happens in a single iteration, this is the big theorem that we proved before. We just have to plug it in here, and then everything works out as desired. So apply the previous theorem and observe that you get the right estimates of the degree. So of the degrees, so you get the sum of the degrees of the mi of the qi's from 1 to j plus 1. That's the sum of I from 1 to j plus 1 of the degrees of the qi's, because we know that this is because we know from the theorem that the q's agree, either from induction hypothesis, we get those from up to j, but then also the next one we get from the theorem. Now this one is bounded by the sum I from 1 to j plus 1, eta of k, because I let the j only run until there, and afterwards I don't continue with the induction of the degree of qi. And the eta of k is defined just exactly by this sum being at most k. And so this means, therefore, that the j plus 1 is still at most eta k, eta bar of k, which is this statement. And this we got from the previous theorem, and this here as well. Okay. So this concludes this argument. And okay, and now we are almost done and can put things together. What we now do is we look at a slightly more fine-grained picture compared to this one. Look at the bigger case. So here is a trace of the Euclidean algorithm. You see it has very long remainders, and you see some kind of triangle that indicates that you won't be able to compute all this area in less than quadratic time, because the area is already quadratic in size. But you see also that the quotients are much smaller. The quotients are just this boundary, and this has linear size. So we are moving in the right direction by focusing on the quotients. Now, how do we get the quotients right? So if we take k sufficiently large, then that means we get roughly the first half of the products right. So here we take this much, so that 2k would be just the degree of r. So 2k would go up to here. But if we apply this reasoning, then this means we will have here an error propagation. We will chop this away. We will not compute this gray part, we will save this time and only compute this part. Okay? But if we have this, that means we have all the quotients up to here. If we have all these quotients, then we can compute also the product of the corresponding matrices that turns the first two rows into these rows. So even if there's no accuracy left, we can restore everything that we have chopped off by doing one big calculation of this product of matrices applied to the first two vectors. Okay, and then I get this, and from this I can then continue. And then it looks like I haven't saved much. I've just saved this triangle, and it is still quadratic in size, the yellow area. But of course, the idea is now to apply this recursively. If I want to get the first half of the quotients, then I will subdivide this further and say, okay, you can get along by first starting with this accuracy, which is now really half of the input accuracy. Then you get to the first quarter of the Q's. With those, you can compute this here. And from those, you can get up to here, and then you can restore again the accuracy that you lost during this approximation, get here, and with this one get here, and then restore and compute. And then you subdivide this further so that in the end you will not see anything yellow in the picture. You will see only computation time that is very tightly sticks to this boundary and is therefore not much more than linear time. Okay, so this is how it works. I'm on the next slide. I'm showing you the algorithm in full detail. Don't get scared; it's a bit lengthy, but it doesn't contain any further ideas beyond those that we have already discussed. So we are already in the process of putting things together and summarizing how everything fits together. So here's the algorithm. It's the fast GCD algorithm. And it takes as input two polynomials. So think of f and g, what they are called here R0 and R1. And they determine a polynomial remainder sequence. They have certain degrees, n0 and n1, they are called here. And the input is also k, and the output is the eta of k. Remember that one of the problems that we had in the beginning was that we don't know how to split the product of the q's in the middle because we don't even know how many there are. So here this algorithm will compute this on the fly. It will of course not see this picture right away, but it will just say, okay, I will start here and then I'll do this computation and then I will see where I end up. Maybe it's a bit earlier or maybe it's a bit later. That depends on how big the degrees of these quotients are. If they are bigger, then this will happen earlier. If they are smaller, then it will happen later. So I'm not taking this this knowledge for granted. I'm not taking it as an input. It's part of the output. And the other part of the output is this matrix R, which turns the input pair into the eta kth row of the Euclidean algorithm. So the k, if we really want to get to the very end, then we will make the k very big, so that this will be the output, the GCD, and 0. But I can as well also take something in the middle, and I will choose a smaller k, and that's what we will need during the recursion of the algorithm. Okay, so the goal is to get the R that turns the first pair into the eta kth pair, where I don't even know in advance what the eta k is, but I will also get the eta k as part of the output. Okay, so it's a recursive algorithm, so there's a base case in the beginning, and the base case here is a little bit more complicated because there are several cases. So it could be that the remainder here is already 0, or that there's a degree underflow, and in this case in any of these cases, you know that you are done. And now here is the problem division. We divide the problem in the middle and say, okay, let's we want to go an amount of k in the sum of the degrees of the q's, but let's first go halfway and say d is half of k, and then apply the algorithm recursively to get a matrix that goes that goes just halfway. So I chop from R and R1 the topmost coefficients, just the ones that I need. So this is what you see here. I'm cutting away everything that is in this area because it's not necessary in order to get to this point. And then at the end of the recursion, I get the R that moves me directly from here to there. And with this R, I will now proceed to compute this part. So there's again, here's a matrix multiplication, matrix vector multiplication. And okay, I fetch a degree of this R. So that's details. Don't worry about these details. That's really technical enough, and not expecting you to see all the to do really go to understand this to check this in full detail, and probably also have some mistakes here. But the important thing is to get an idea of how this algorithm proceeds. So here we are coming back from the first recursive descent, and then we are restoring the accuracy that we lost during this computation by checking what would be in this row if we had computed directly with higher accuracy, with 2k instead of 2d, which is just half as much. And then I check whether I'm done. So if the rj is 0 or the k is less than what I want to achieve, then I'm done. And this matrix already does the job, and the eta is the j minus 1. And otherwise, I do a division step. I compute explicitly the quotient here, and also the remainder, and do one step in the Euclidean division, and then I get a new d, and the new d, that's the rest of the d, and it's not k half because I'm doing here a division step. So it's k minus this degree from here minus the degree difference of those two that I have restored. And then I do a second recursive call that corresponds in the picture to this one here, where I get then down to the rest, to the bottom of the triangle. Okay, and then from this recursive call I get another j and another d and another matrix, and the final result is then the eta, which is obtained from the j from here and the j bar from here, and the r, which is obtained by the first matrix multiplied by the matrix that corresponds to this quotient multiplied by the matrix that comes from the second recursive descent. So it's quite complicated, and it's a pain to program it and to get all these indices right. But if you get it right, then it's really fast. So here's again a tree. There's always a tree when you have a recursive algorithm that splits the product in the middle. We had a multiplication tree last time in the context of evaluation and interpolation, and we have such a tree now. But the tree now is a little bit different because before we had all the factors of the multiplication tree at the bottom of the tree, and then in the middle of the tree we just had these products. But now we have ones at the bottom because we are doing nothing here. In the base case, we just return the identity matrix, and the things that I want to multiply are distributed over the internal nodes of the tree. So that's just a minor difference, but it's a difference. And what happens then in the algorithm is that one recursive call computes this entire product, and the other recursive call computes this entire product, and then at the bottom, when I'm combining the things here, then I'm multiplying this, and in the middle, the queue that is at the top of the tree, this one. So I'm computing this matrix the matrix product of those ones times this times the matrix product of those ones. When I now have read the product from right to left. All right. It is unnecessary at this point to argue that this algorithm is fast. It requires a computation time of m of k log k operations in the ground field, and that's again a world record. The argument is the same as before. There's this recurrence that says the runtime in terms of k is bounded by the runtime of two recursive calls plus the runtime of a single multiplication of size k. Let's see where the multiplication is. There are several multiplications actually. So here's one recursive call, here's the other recursive call, and they are all of half the size, roughly half the size. And where are the multiplications? Here is a multiplication, and here is a multiplication. This division with remainder is a multiplication. And then here in the end, when I combine the results, that's also a multiplication. But all these multiplications have the required size to justify the correctness of this recurrence. And from this recurrence, you get this complexity for the same reason as we have seen several times. Okay, so that's it. Fast Euclidean algorithm. We can compute the GCD of two polynomials in essentially linear time. To conclude, I just want to make a couple of remarks about this algorithm. So the first remark is that the algorithm, as I formulated it, takes k as an additional parameter. The user doesn't care about k. I need this k only as a recursion. So the user will take the degree of f as k, and then apply the algorithm as specified. There's another technicality that I assume the degree of R0 to be greater than the degree of R1. But if that's not the case, then you do just one division step before you apply the algorithm. This one division step will take a linear amount of time. So, and you do this only once, so it's not going to mess up your total complexity. Another interesting observation is that we started out by saying we want to break this product in the middle. Now, what really means in the middle? It could mean that we break the product such that there are as many factors on the one side as on the other side. But if you look very closely into the algorithm, then you see that this is not really what we have done. We have done something that is even a little bit better, because we have also taken into account, and I didn't emphasize it to keep it simple, but now is the point to emphasize it. We have also taken into account that these polynomial matrices may be matrices of different degrees. So remember these Q's were the matrices that had the quotients in the lower right entry, 2 by 2 matrices. And the quotients usually have degree 1, but not always. And it could be that maybe you have such a product of 100 matrices, but the first 50 of them have very high degrees in the Q, and the later ones have very low degrees in Q, and then it wouldn't be a good idea to split the product in the middle, and you would rather split it closer to the beginning. And that's what we do. What we do is we break this product in such a way that the sum of the degrees on one side is roughly equal to the sum of the degrees on the other side. And that's even better than just blindly splitting it in the middle. Because what we want is, in the end, in the combination, to have a balanced product, so that fast multiplication works very nicely, and we have a fast product, a balanced product. We have better chances to obtain a balanced product if we distribute, or if we split this product so that the degrees on one side are equal to the degrees on the other side. Another remark is that you can compute not only the GCD very quickly with this algorithm, but you can compute any row in the polynomial remainder sequence. So that might be useful, for example, for rational reconstruction, as we discussed when we talked about computation in homomorphic images. When you want to recover from a homomorphic image the rational function that led to this image with a small numerator and the denominator, then you would take a remainder in the polynomial remainder sequence that is somewhere in the middle, and you can compute this also quickly. What you can not do, however, is compute all of them, because that would mean you compute the entire yellow triangle, and the triangle has a quadratic size, and a quadratic size is something that you cannot expect to be able to compute in less than quadratic time. Here's another fun fact. So you can you maybe remember that we had this operation of reversing coefficients. We needed this in the context of fast division. So this ref just takes the polynomial and puts it upside down. And there's a fun fact that says that if h is the GCD of f and g, then the reversal of then the reversal of h is the GCD of the reversals of f and g. And depending on how circumstances are, it may be that this here is easier to compute than this one. So possibly not in theory, because in theory we care only about the degrees, but maybe you're working over a field that is complicated. So it's maybe think of the rational numbers instead of a finite field where everything is equal cost. But if you have something like the rational numbers, then maybe the trailing coefficients of f and g are simpler than the leading coefficients. But if you enter into the Euclidean algorithm, you will first hit the leading coefficients, and you want to keep the things small as long as possible, unless you do Chinese remaindering and homomorphic images, which you should do anyway. But if you don't want to do this, then you can use this to put f and g upside down, work with the smaller coefficients that are then at the top if they previously were at the bottom, and then afterwards reverse again to get the h. But that's just an optimization that you will probably never use. I just wanted to mention it because it's somehow funny. More realistically is, or more importantly, is that if you have an infinite field of coefficients, then you have to deal with the expressions well, and you can do this by using homomorphic images. That's always a good advice, but you should also be aware that in this polynomial remainder sequence you have the problem that the remainders are the remainders are uniquely determined, but the information that they carry and that is interesting to us is only relevant up to a multiplication by a constant. So if you do a Euclidean algorithm for polynomials over the rational numbers, and you really don't want to use homomorphic images for some reason, then you must ensure that you always divide the remainders by their content. Either make them monic or make them integers and monic and primitive, because otherwise you'll get the remainders multiplied by a huge number that is completely meaningless and that slows down your computation to the extent that you can't finish it because you'll get an expression swell that is exponential, and after a few steps your memory will be filled up with lots of garbage that has absolutely no meaning. So be sure that you always do uh, division by the content of the polynomial if you really have to work over an infinite field. And the point here is that you can do this not only in the classical Euclidean algorithm, but you can also do this in this fast version that we have discussed today. And finally, there's also an integer version of this algorithm. This integer version, so that's an algorithm that computes the GCD of two integers with n digits. And the complexity of this algorithm is also multiplication time times log, where here the multiplication time is, of course, the integer multiplication time, the time that you need to compute the product of two integers with n digits. Okay, and once more, a remark that I made already at the end of last video when we talked about evaluation and interpolation. We have here a complexity of m of n times log n, and m of n can be smaller than quadratic, and in this case the GCD computation is also smaller than quadratic. But if you use this algorithm that we discussed today in combination with the classical multiplication methods, then there's no speed up whatsoever. It actually gets a little slower. So it's again so that we have not really found a cool improvement in the GCD computation itself. Instead, what we have done is to shuffle around the work from one side to the other, and we have pushed as much work as possible into the multiplication, and then rely on the speed of multiplication. Okay. So this is the end of the discussion of the Euclidean algorithm, and in the next video I'll show you an algorithm for the fast square-free decomposition. So this is now going towards the end of the second part of the course, and to the beginning of the third part of the course, where we'll talk about factorization of polynomials, but here the transition is a little bit more smooth. So the next lecture is already a little bit into the direction of factorization, but the focus will still be more on efficiency. Okay, but for today it's enough. Thank you for watching, and see you again next time.